You are holding two wet prints. One is a frog, one is a cat. A camera does not know the names. A camera only records light, red, green, and blue numbers packed into a grid. Your job tonight is to teach a model to read those numbers and say frog, not cat. We will do that in PyTorch from a blank notebook to a trained vision net you can actually run. This studio is Safe Light Press, a dark room, a torch on the wall, trays of developer on the bench. The torch is PyTorch. The print is a tiny color photo. The wash is training. We will not start with clothing, and we will not hide behind a one-click fit button. PyTorch wants you to see the loop: forward, loss, backward, step. That is the craft. Picture the path before we type a line. First we load photos, then we turn them into tensors. Then we stack a small convolutional net. Then we pick a loss and an optimizer. Then we run a training loop. Then we test on photos the net has not washed before. If you skip that order, you will paste a tutorial and not know which line actually learned. So why PyTorch at all if you already saw TensorFlow? PyTorch feels like ordinary Python. You run a line, you get a tensor, you print it, you keep going. That eager style is why beginners can debug. The print is honest, the shape is sitting there. A model in PyTorch is a class. You inherit from n module. You name the layers in init. You send data through forward. TorchVision is the vision shelf. Datasets, transforms, and common photo nets live there. I want you to hear the official sentence, not a slide I invented. On the Training a Classifier tutorial at PyTorch.org, they say this. For vision, they built a package called TorchVision with loaders for ImageNet, CFAR10, and MST, so you do not write boilerplate. Open that tutorial later if you want the same official net. Tonight we will walk it like a teacher beside you. CFAR10 is our print pile, 60,000 Technicolor photos, 32 by 32 in 10 classes. Airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. 50,000 for training. 10,000 held out as a test the model must not memorize. Each photo is 3 channels by 30, 2 by 30, 2, color, not gray. That is the whole sheet. A dense net that flattens those pixels can still guess. A convolutional net looks at neighborhoods, which is how photos actually work. Convolution means a small filter slides across the print and votes for a local pattern. An edge, a blotch, a wing. You do not draw the frog by hand. The filters learn the pattern. Alright, open a notebook. Name it SafeLight Print, one idea per cell. First cell is only the imports. Type import torch. Then import torch, none as n, that is the layer chef. Then import torch, n functional as f, that is where relu lives as a function. Then import torch, optim as optim, that is Adam and also stochastic gradient descent. Then import TorchVision and TorchVision, transforms as transforms. Then from torch utils, data import data loader. The loader is how batches walk into the loop. Print the torch version so we know the install actually loaded. Run that cell. QD logs are normal. Wait until the prompt comes back. If torch imported, the torch is on the wall. If it failed, fix the install before you touch data. Next cell is the transform. A photo on disk is not a tensor yet. Transforms composes a list of steps in order applied to every print. First step transforms to tensor. That turns a PL image into a float tensor and scales pixels from 0 to 1. Second step transforms. Normalize with mean 0.5 and st 0.5 on all 3 channels. After that normalize, a pixel that was 0 becomes -1 and a pixel that was 1 becomes +1. Why bother? Nets train more kindly when the numbers sit near 0 not up at 255. Name that pipeline transform. We will hand it to the dataset, not run it by hand on each file. Now the dataset equals TorchVision, datasets. CFAR10, root is a folder named data, train equals true, download equals true, transform equals transform. That one call fetches CFAR10 if the folder is empty, then wraps every training print in your transform. Test set is the same call with train equals false. Same folder, same transform, different split. Print the length of train set. You should see 50,000. Print one sample. Image label equals train set of 0. Shape you want 332 to 32. Channels first, that is PyTorch layout. PyTorch vision tensors are NCA batch. Channels, height, width, not height, width channels. If you later plot with matplotlib, you will permute those axes. The model does not. The model wants channels first. Print the label, it is an integer from 0 to 9. 0 is airplane, 6 is frog, 9 is truck. The class names are a tuple you keep beside you. Plane, car, bird, cat, deer, dog, frog, horse, ship, truck. 32 by 32 is tiny. A frog is a green blotch. A ship is a hole on water. That coarseness is a gift you can train on a laptop. You can still see the idea. Now the data loader. Train loader equals data loader of train set, batch size 64, shuffle true. Shuffle true means each epoch walks the pile in a new order, so the net cannot memorize the sequence. Test set loader is data loader of test set, batch size 64, shuffle false. Test order does not need to mix. Num workers on Windows can fight you. If you see a freeze, set it to 0. The tutorial says the same thing. Pull one batch. Images labels equals next of 8 of train loader. Print images. Shape you want 60, 4, 3, 32, 32. That is one tray of prints. Print label shape 60, 4 integers. One name per print. That batch is what the net will see in one forward pass. Let us talk about the net before we type the class. A fully connected layer looks at every pixel talking to every neuron. Fine for tiny XR. Wasteful for photos. Neighbors matter. A frog eye is a local clump. A truck wheel is a local clump. Convolution looks locally. Conv2D needs in channels, out channels, and kernel size. In channels is 3 because this print is red, green, and blue. Out channels is how many filters you learn. 6 is a small start. Each filter hunts a different local pattern. Kernel size 5 means a 5 by 5 window. It slides, it votes, it writes a new map. If you do not pad a 32 map becomes 28 after a 5 by 5. The edges get eaten. Then max pool 2 by 2 halves the map. 28 becomes 14. Then another conv, then another pool, and you land on 5 by 5. That is why the official tutorial flattens 16 times 5 times 5. The geometry is not magic. It is the leftover grid. I will type the official style class so your notebook can sit next to the PyTorch org page. Open the class, name it tinyCNN and inherit from NN module. Define init with self, then call superinit. That hooks your class into the module machinery, so parameters are tracked. Self conv1 equals n, conv of 3 is 6, 5, 3 in 6 filters, window 5. Self pool equals nen, max pool 2 of 2, 2. A 2 by 2 window, stride 2. Keep the strongest vote in each square. Self conv2 equals n, conv of 6, 16, 5. 6 maps in, 16 maps out, window 5 again. Self s1 equals nen, linear of 16 times 5 times 5, then 120. That is the first dense reading of the flattened maps. fc2 equals nen, linear of 120, 84. fc3 equals nen, linear of 80, 410, 10 scores. One per class, we call those logits. No softmax in the net. Cross entropy will do that math inside the loss more stably. Now forward. This is the path 1 batch walks. X equals self pool of ReLU of self. Conv1 of X filter curve, then shrink. Then the same pattern again. X equals self, pool of ReLU of self. Conv2 of X. Then X equals torch. Flatten of X 1. Keep the batch axis. Flatten the rest into one vector per print. Then ReLU of FC2. Then FC3 with no ReLU. 10 raw scores come out. Return X. That is the whole forward. No training happens here. This is only the recipe for one pass. Let us walk those lines again, because this class is the model. Line 1 of init, super init. Without it, PyTorch cannot find your layers when you call parameters. Line 2 conv1. This is the first look. Local windows on the raw color print. Line 3 pool. This throws away exact position a little and keeps the strongest local vote. That is how a frog can sit left or right. Line forward conv2. A second look now on the first look's maps. Patterns of patterns. That is depth. Then the 3 linear layers. Once the print is a short vector, dense layers can vote for a class. Forward is not a second list of layers. Forward is the order. Init names the tools. Forward uses them. If you name a layer in init and never call it in forward, it still sits in the file and it never learns. Make the net equals tiny CNN. You should see conv1 pool, conv2, FSC1, FCC3 with their shapes. Now the device equals CUDA if torch. CUDA is available LCPU. On this lesson machine we may be on CPU. That is fine. The loop is the same. It is only slower. Net equals net. 2 of device. Layers and weights must sit on the same device as the batch. If the batch is on CPU and the net is on CUDA, you get a device mismatch. Move both or move neither. Loss next. Criterion equals nen. Cross entropy loss. Cross entropy wants raw logits and integer class labels. Not one hot. Not probabilities you softmax twice. If you softmax in forward and then call cross entropy loss, you will double the squash and the loss will lie. Optimizer equals optim, atom of net. Parameters, learning rate 0.001. Net, parameters is every weight the module tracked. Atom will nudge those weights using the gradients. Stochastic gradient descent is the older cousin. Atom is a kind default for a first vision net. Either can work. Here is the training loop. 5 beats. I want you to say them out loud. First optimize 0 grad, wipe old slopes. Gradients accumulate by default. If you skip this, yesterday's slope piles on. Second outputs equals net of images, the forward pass, 10 scores per print. Third loss equals criterion of outputs, labels, 1 number. How wrong was this tray? Fourth loss backward. Autograd walks back through convent linear and fills, grad on each weight. Fifth optimizer, step. Adam reads those grads and moves the weights a little. That is one batch. An epoch is every batch in the loader once. Let us type the loop in the notebook, so the 5 beats are not a poster. For epoch in range of 2 epochs is a short wash. Enough to see loss move, not enough to win a contest. Running the loss equals 0. We will average it so the print is readable. For images, labels in train loader. That is one tray at a time. Images equals images. 2 of deviables equals labels. 2 of device. Same bench. Type optimizer. 0 grad. That wipes yesterday's slopes before this tray. Then call the net. Outputs equals net of images. Then the loss. Loss equals criterion of outputs, labels. Then rewind loss. Backward fills a gradient on every weight. Then take the step. Optimizer. Step moves those weights a little. Running the loss plus equals loss item. Item pulls a Python float out of a one element tensor for printing only. After the inner loop, print the epoch and the mean loss. You want that number to fall. If loss is not a number, you mix types or you send probabilities into cross-multiply loss. If loss sits still, check zeroed, grad, check the learning rate, and check that you actually call backward and step. Fit is not a Keras verb here. You are the fit. The for loop is the fit. After training, switch the net eval. That turns off dropout and tells batch norm to use running stats. We did not use dropout tonight. Eval is still the honest habit before you score. Torch, not grad, is a context that says, do not build a tape. We are only reading, not learning. Inside that, walk the test loader. Compare argmax of outputs with the labels. Count the hits. Accuracy is hits divided by the test size. Random among 10 classes is 10%. You want well above that. On a 2 epoch tiny net, do not expect a contest score. Expect a curve that fell and a guess that beats chance. Now one print. Pull a test image. Send it through the net. Softmax the logits only when you want to read probabilities out loud. Argmax of the scores is the class number. Look it up in the names tuple. Say the word frog, ship, truck. If it is wrong, that is still a trained net. The wash was short. The print was tiny. The lesson is the loop. I will show you the same loop in Visual Studio Code as a script named SafeLight print. A notebook is for seeing. A script is for repeating. Same class, same 5 beats, same device move. Watch the file, not a screenshot of someone else's collab. Common traps. I will name them the way they actually bite. Trap 1. Channels last. You plotted height with channels, then fed that tensor to conv2D. Conv wants channels, height, width. For getting 0 grad, loss looks wild. Grads pile up. The torch is not broken. The tray was dirty. Trap 3 labels as floats or as 1 hot with cross entropy loss. It wants class integers. Calling softmax, then cross entropy loss. Squash twice, loss lies. Keep logits in the net. Trap 5. Training waits on CUDA and forgetting to move the batch. Device mismatch, move both. Trap 6. Testing while the net is still in train mode after dropout later. Tonight we skip dropout. The habit still matters. Eval before you score. Trap severing loss item as the only success. Watch test accuracy 2. A falling train loss can still be memorizing. Let us recap the darkroom not as a list you chant, as the order you will type tomorrow. Import torch, NN and TorchVision. Compose to tensor and normalize. Load C, far10. Wrap it in a data loader. Build a module, conv pool, then flatten, then linear to 10 logits. Cross entropy, Adam, then the 5 beats 0 grad, forward, loss, backward, step. Move net and batch to the same device, eval no grad argmax. Read the name out loud. When a print comes up wrong, do not throw the torch. Print the shape, print the device, print one label, then look at the 5 beats. Hang the frog print on the line while it is still wet. If a new frog still reads frog after the wash, you did not copy a photo. You taught a torch how to look